Okay, raise your hands if you are a PhD student or postdoc. Nice. What about masters? Oh, so the majority is basically graduates. Do we have any undergrad students in here? Well, I appreciate you. Because, you know, at Queens, don't hold it against me. I'm a Queens graduate. There's usually quite a little bit of rivalry between Queens and Western. But I used to manage last year of my being a PhD student at Queens. I used to coordinate these seminars and talks for undergrad and graduate students. And the trick was pizza. So every week, every Thursday, I would say, well, welcome pizza consumers. At least if you don't like the talk, there's going to be pizza. But I think it's after lunchtime. So I really appreciate it because we're not getting it with pizza. It's like pure, genuine interest.
They made us mandatory. They made us mandatory.
Yeah.
Independence with the QR code. Big attendance. More important than pizza. Stick, not the carrot here.
Okay, so we got different strategies at different universities then. All right, my name is Saeed, and I'm very happy to be here. Thanks for coming, not for the pizza, but for the QR code. I hope there's something that you're going to get out of this. This is just a conversation opener between you and me. Just so that I can introduce myself. And it's nerve-wracking. You know why? Because it should be when you're getting yourself up in front of smart people. There's always a huge chance they're going to ask very serious questions and poke holes in your theories and whatnot. So that's the challenge that I'm up for today. In front of the, you know, smartest people probably in the country. Pure talent, but we're all working on our skills. Let's not forget that. I'll talk about hydraulics today. But the major things that I'm going to talk about, the things that I'm going to talk about would be applicable to any sort of engineering projects, engineering challenges, different fields of engineering, because in real life, when we're doing work, we can only deliver great, valuable work in big teams. No one has ever achieved anything individually, right? And when it comes to groups and teams, it's different realms of civil engineering, and not just civil engineering. You're going to have to work hand in hand with chemical engineers, mechanical engineers, electrical engineers, architects, and so on. So I hope, you know, we're not going to get super bogged down with the hydraulics and like some theories, but the main things that I'm going to talk about should be applicable if you're looking at engineering projects in general. You want to start working professionally. And it's also a gateway between you and Jacobs Engineering. I'm today representing Jacobs. And you can always find me on LinkedIn, or you can ask Big for my email address. And from there we go. because we're always growing and we're always looking for talent. So there's pure talent. So have that in mind as well. Yeah, basics of hydraulics for engineering professionals, civil engineering professionals, and student. Yeah. Okay. So I'll brag about myself a little bit. Don't worry about it. You can sleep for that part. We're going to talk about engineering, the nature of engineering work nowadays. We get focused in civil engineering, water, hydraulics, my niche, or a lot of people's niche. What is the model? You know it. Don't worry about it. Why we use models. And then we're going to talk about my bread and butter. I spent probably like 6 years in water distribution systems during my master's and my PhD to look at energy efficiency, how we can make these systems a little more efficient, and to just figure out where the energy is lost. All right. We're going to talk about not my stuff, but like water distribution, pressurized hydraulics. And then we're going to talk about wastewater, gravity hydraulics, something that I have developed in myself in terms of my professional work. So academically, I'm more like water distribution, but professionally, I do a lot of work in gravity flows. How models are developed before they can be used, the models need to be calibrated. It's quite an interesting topic, but I'll just touch on it. Beyond modeling, some to-do list for you. You would want to develop yourself in hydraulics or even in sort of sub realm of civil engineering. Some brutal facts about the consulting work, not to discourage you. As I said, we're always looking. Just some points to consider if you would like to apply to consulting work in the engineering profession, how you can learn more, some more resources for you, and hopefully we can have some time for questions. So I'll do this. By training, I'm a civil engineer. Everybody's in civil engineering here, right? Yeah. Yeah. Good. From University of Toronto, where I was born and raised, and I worked for a few years. And then I moved to Canada in 2013. Before that, I did the master's from the same university. You can see the topic, energy assessment of, pumping stations, how they should be throughout the day into a distribution system that brings drinking water from the treatment plant to the houses where we live. And then I looked at energy again between 2013 and 2018 at Queen's University. It's not that bad, but I looked at energy efficiency, but not at the pump stations. I looked at each and every single pipe because that's where the energy is lost. Okay. And for that matter, I had to use a lot of statistical analysis. Okay. Well, that's my PhD. I looked at that. It's quite fun. Then I became a professional engineer because toward the end of my PhD, I was working full-time in Toronto and part-time. Yes, that's a possibility, PhD students, if you're thinking. There's not only one way of living. You don't have to work full-time. If you're kind of through with your PhD, which was the case for me, I was lucky. I got the permission from my supervisor and I moved to Toronto, worked full-time, and I part-time wrote my thesis. Getting a PhD, getting some professional experience. So right after 1 year, I got my PhD with Professional Engineers Ontario. And then because I was interested in bossing people around, I'm just kidding, I thought maybe project management and people management would be something that I would want to learn a little bit more about. So I sought after some kind of training, like official project management training. That's how I got my PMP, project management professional, with the global PMI. And I'm also an adjunct professor in a university in Iran, directing master's students, co-supervising, not on my own, but helping other faculty members. I've been in consulting since 2008. It's been a weird mishmash of working full-time, doing research full-time, but it's been always together and absolutely my research. So if you ask, what I'm doing, I don't know, I'm just doing both. And it's worked for me at this point. I've been with the gigantic Jacobs since 2017, one of the biggest engineering firms in North America and the world, mainly looking at hydraulics. But this time, not just water, as I got my, academic training in, but in wastewater, stormwater, pipes. We're going to look at the pipes mainly because civil engineering and the topics are so broad. The breadth of things you can be focused on is just endless. Look at master planning, look at how the growth is going to be within the next 10, 15, 20, 30 years, how the growth is going to happen, how we're going to adapt hydraulic municipal infrastructures with the growth that is bound to happen based on planning from the municipal clients. But I don't know why I'm repeating this academically, mainly a water distribution system, more specifically energy. You can just check out my publications. And I guess in combination, like I got over 30 publications, mainly in water distribution system, probably a couple in sanitary that I have recently published. You can check them out. But enough about me. These days, if I want to tell you something, I'm pretty sure a lot of you are coming back from industry just for higher degrees. So you already know that. But everything is like super computer dependent. Now you're taking your courses. I don't even have to talk about that. But it is interesting that you can just stay at home. That's how I work. I'm working from home every day. Communications, meetings, collecting information about infrastructures, making decisions, running models. Everything is through computers. So make sure that there is a niche that you've got through computers. And obviously, graduate school gets you ready. You're going to work on a specific project that you're going to master. And that's going to be your gateway. But here's the thing. Everybody wants you to look at more and more combinations, alternatives, simulations, because you're using computers as opposed to 30 years ago, 40 years ago, even like 20 years ago, where software packages were not that really dominant. They want you to look at more and more simulations to not only find a solution, but also the best solution. So what's happening? The computer's doing the dirty work. What the computer is not really able to do, never ever, is the engineering judgment, because it doesn't have a brain, it doesn't have a heart. You're going to have to use your engineering judgment. You're going to run a simulation, you're going to look at the results, think about it. Run another simulation, another alternative. And I'm going to talk about that. What do I mean about simulations and alternatives? Okay, they're like, what if? What if this happens? What if that happens? What if things change unexpectedly? The solution, the calculation is by the computer. But you're going to think to make the final decision. That is what's happening in engineering. What we tend to forget. we just want to look at the bottom of the spreadsheet to see the last number. We just want to look at the model results and but we're just one step away if we're not very careful. We got to make the engineering decision. That's the, front line. That's the most important thing. So I think I already covered all the bullet points that I have in here. So today, water and hydraulics, a small part of civil engineering, as a big team, we're together looking at different realms of civil engineering. One is water. Under that, there's hydraulics, there's hydrology, and I'm not saying that the list is exhaustive in here. There are a lot of different things, niches that you're working on, and you might be like, my research topic is not really included in here. And you're right, because I'm just going to focus on hydraulics of not rivers and hydraulic structures, but conduits. And in the conduits, we use pipes between the water treatment plant and the houses to bring the water, drinking water, to the houses grab drinking water. And also there's pipes between the houses and the wastewater treatment plant that collect the sewage. Okay, so we're going to talk about those. Hydraulics is definitely way broader. And when it comes to like conduits, we're mainly interested to know the regime of the flow, or like how the flow is changing in terms of what is the flow rate, what is the HGL. These are the most important things. Okay. HGL, and then in the pressurized systems, it's likely different from gravity flows. Okay. They'll have that in mind, and then we're going to talk about it a little more. As I want to just cover the basics, we all know what models are. And models could be like prototypes that we use in a lab, or the kind of model that I'm talking about would be virtual in a computer. Let's say if I did 2 theses in water distribution system, I really didn't mess around with the real distributions. I didn't go out, like dig out the asphalt and like dig into the to a pipe to break it to like do tests on it to see how the energy is changing. But instead I used a model of the distribution system of, for example, the city of London, the city of Kingston, Ontario, or Columbus, Ohio, as I really work. So have that in mind. And those models would represent the reality that we're trying to get to know how it would behave. Okay, so, and I trust that every day you're modeling a bridge or a structure, foundation of something, or a pipe, or I don't know, whatever that your riverbed, like the little flume that you're modeling in the lab. We're always using models, and we want to look at what happens if. That's why we use models. Basically, we want to say, we're not going to wait in the city of London 25 years and see what happens in 25 years when the population has grown to double. But no, we're going to look at the model. We're going to take the existing model of, for example, the distribution system of the city of London, and we're going to put the population of 25 years from now on it to run and see what kind of catastrophe we're looking at now, so that we'll be ready in 25 years. That's how we've always operated these systems. We look at what happens where there's a fire. What if we're going to get a fire? Are we able to find that fire? Is the distribution system able to find? What if there's going to be a lot of rain tomorrow, as it seems to be quite a bit of rain today? Are we going to get some sort of flood somewhere, something like that? There are two approaches. You can wait and see until you're in big trouble, or you can get yourself ready before it happens. That's why we use models. Now, we're getting smarter. We're developing some sort of resiliency in the municipal infrastructures that we're operating by looking at the problems, asking those what if questions before those undesirable situations actually happen. Okay. And obviously, it is going to be, yes, it works. Obviously, it's faster. It is safer. I'm not using it. I'm just going like this. It is faster. It is cheaper, and it's not destructive. Like sometimes we don't have to set the whole city on fire to see what happens here. My distribution system ready to handle a fire. You don't have to set a fire. We can model a fire, which is quite nice. And in some cases, it's not feasible to wait for, I don't know, like 100-year storm that may or may not happen in the next 10 years to see what happens. But you can always model and see the bad consequences. Right, is next. Oh, we did. Okay, so pressurized hydraulics. I'm going over the basics, and if it's a little, God, just don't waste my time. You're gonna meet. It is interesting because sometimes graduates, even from major universities, they come out and they quite don't know the difference between gravity and pressurized hydraulics. And that's fine. And that's why I talk about it for a minute. Okay. So what happens is the HGL, hydraulic grade line, in a pressurized system, it's quite nice because when you're walking out on the street, and this is your building, you just got out for a little walk, not today, it's nasty. Say tomorrow, in 2 days, we're gonna go for a walk. You're walking along the, sidewalk. First of all, you gotta know that under the asphalt, there are a lot of pipes. Some of them are bringing water to our houses. Some of them are handling sewage or stormwater, gas pipelines, a lot of different things. Well, we're talking about water and wastewater today. It's interesting for water. The HGL, you don't see it, but it's above your head. Why? It's out in the sky, usually 2, 3, 4 floors above your head, because these systems are pressurized. When you open the water tap, the water needs to get out of the water tap. So sometimes when there is a break in the pipe, that if it surfaces at all, you can see something like that. You can see how high it could go. So what is the difference of that? And okay, I was going to get ahead of myself. So here is one of the most important slides for you. If you don't like my lecturing style, absolutely fine. But let's not forget the software packages that we expect you to be familiar with. If you get a chance between today and the day you want to get hired, okay, to experiment with some of these software packages I'm about to talk about. Water Gems by Bentley. Some of these are, you have to pay for the license. As students, it's hard to, get your hands on. And that's totally understandable. There are two ways. There's a surrogate software I'm going to talk about, EPANet. I wrote 2 theses with that dinky software package. But there are sometimes opportunities through university, you can get like student license or something, if there's like enough of you, you know, asking for it, he could have it. And I'm not saying if you don't have the experience, we're not gonna hire you at all. No, but it's gonna give you an edge over the people who are not like, do you know this software? No. Do you know that one? Well, if you wanna, if you're interested in something, at least you can try that, or like, you know, watch some videos about WaterGens. So WaterGens is very friendly. It's like CAD based, like the way it looks and how you zoom in and zoom out. GIS capabilities, you can like bring your GIS elements into it and build a model very quickly. And so the best and the most expensive, biggest municipalities, City of Toronto, Peel Region, City of London, York Region, they all use InfoWater by the company Innovise. Big municipalities, big complex models. If you know those, you know how to work with InfoWater. We don't expect, don't get me wrong, not here to discourage you, but if you are familiar with that, you're golden. To me, you're golden. Okay. And last but not least, EPA net by US EPA. It's open source, it's cheap, 1.5 megabytes. Download it as we speak. You can download and get it running on your laptop. Open source, so just Google around and you can figure it out. That's how I did. Wrote two theses. I used my own codes to manipulate it, but you know, it's a good start. And once you're familiarized, you've got yourself familiarized with those software packages, there is one more pressurized phenomenon you can do. Have you ever heard of transients of water hammer? Well, maybe some of you are working on it, like as research topic or something. Some people work on it, you know. When there's a sudden change in a pressurized system, the system goes crazy. It goes crazy, like ups and downs in the pressure. It's just, you know, I'm going to explain it like this. There's a steady flow, like a normal regime of flow in a pipeline with a valve on it. Now it's going from left to right. And then I'm bored and I just shut the valve off. Sudden change in the system. It happens. Nobody does it, you know, on purpose, but sometimes when you break in huge facilities like a pump station, or the operator, you know, now these big facilities are all computers and like sensors, and sometimes things go wrong. The valve's closed, the water that used to a second ago go from left to right, it is stuck. What we're going to do, the train that, you know, as an example, if it's a train, is just getting stuck. It just wants to keep going. And naturally, the pressure, look, the pressure was like around here, and the pressure has been accumulating. It accumulates and accumulates, and it has to go somewhere. It either goes somewhere or this happens. Big pipelines, very expensive, you know, pumps or pipes or whatever, assets, let's call them assets, because we're all paying for those, by the way, through our tax money. So we should care about pumps and pipes and everything and how they're being modeled and optimized or operated or whatever. This wave goes back and forth throughout the pipeline until it is going to break, find somewhere, some hole that it could go out of, and it's going to break and like explode from that part to pressure that's accumulated to get dissipated naturally, which is not very natural. So this is one of the coolest things you can do in pressurized systems. And once you do it a few times, you'll see that it's not really rocket science, but it's a very sought after skill. So Hammer, which is the name of the software, is something that you would want to look at again by the software Bentley, but you want to have some previous experience in pressurized systems a little bit, and then you can probably experiment with transients. By the way, transients is the way we engineers say. If you open the dictionary, it's transient. But if you say that as the engineers in the office, they're not going to talk. It's like two syllables, transient, which means like a transitory state, something just like we started talking about it. We say transient. Engineers are not necessarily very good at pronunciations, but that's gravity flows. Unlike the water systems, pressurized systems, gravity flows when you're out for a walk. You want to go for a walk today, I'm fine with it. Again, underneath, there is sewer pipes or supers. The water, the wastewater, stormwater flowing through them. But the HGL is now underneath the asphalt, below your feet, because they're not pressurized. Those systems work by gravity. When the start of the pipe is higher, the end of the pipe is lower. How water travels. All right. So, cool thing. I thought I would mention it because I've seen graduates. Okay. Come. Okay. Software packages. Again, if you don't like my stories, you'll have access to the slides afterwards. I'll share with Professor Lee, and you can ask for those for sure. Info works by Innovize. Again, big municipalities. If you know that, you're golden. SWIM by US EPA, just like EPANet, open source. Used in academia. Try it now. Few megabytes. You can experiment with it. That's your gateway. PC Swim by CHI, who used it recently, or medium-sized municipalities, sewer gems, just like the counterpart of water gems, CAD based. Okay, I'm just speaking of it. I was not aware of it. Yeah, no problem. How we develop models. We don't sit down and put all the elements together. Usually, if there's not a model, the municipality, small municipality, they want to develop a model for the first time, they have a GIS system. They have put all their assets in GIS. So that's, it stands to reason for you to get yourself familiarized with ArcGIS or anything like that. If you can manage, I'm pretty sure that you'll have access through university. Once the elements are put together, the hydraulic loads are usually communicated to you through Excel spreadsheets by the historical data, or every system is always monitored through SCADA. What is SCADA? Supervisory control and data acquisition. These pump stations, these big assets are always being monitored. The flow that is going through them, the pressure that they're putting into the system are always monitored. That is used. So we get that data and put it in the model. Elements from GIS, loads from SCADA, or any sort of historical billing records. The model is shaped up. Please. No. Don't want to work. And then Once the model is built, I'm afraid I have to say it's just a storage unit of information if you don't calibrate it. Because there's no reason it has to show the exact behavior of the real system that's outside in the real world. What am I going to do then? We're going to monitor the system, the process is monitoring the system, and tweak some parameters in the model to minimize the difference between the model and the field data. That is very crucial. Okay, that is called data or model calibration. What's required? Yep, you go out in the field, some strategic locations. You're gonna monitor the flows and pressures, and then compared to the model, I'm not going to go through that, but that field data is very important. The quality of the data, because you're going to calibrate your model to the data. If your data is not of high quality, your model is supposed to represent the reality. It's not going to be of high quality. It's a very sad fact, or it's reality, but it happens all the time. We're always limited, you know, because of some sort of problem with the contractor, some mistake that they made out on site when they were collecting their data. The calibration procedure will be common. And usually when you're collecting your field data, here's the catch. You start monitoring. If it's a pressurized system, like a distribution system, or gravity system, like sanitary system, you start monitoring the flows or pressures. Some, you know, so you scatter your monitors around the system and then you shock the system. In water distribution system, what we do, we open up the hydrants, the fire hydrants that you've seen, we open them up, and then that's a little shock, pressure drop, and the monitors are monitoring the effect of that pressure drop. And that's what you want during calibration. In this gravity systems, during an extended period of time, you collect data and you hope for a few days of no rain where the system is going to dry up to see those minimum low flows. And then you hope for some, you know, good rainy days, some flows in the system, how the system is in different places would react. And then you'll collect all the data, bring it into the model, into the calibration. That's going to be a good calibration. Okay. So that's how it's done, folks. Once you've done that, accolades are the heart of modeling to me is calibration. You usually start with smaller assignments. You don't delve into calibration because it could be overwhelming. But once you've calibrated a few models, great job, because you're perfecting your understanding of hydraulic modeling. And it's not just about hydraulics, any sort of model that you're given for structural analysis, geotechnical analysis. It is a good question to ask, you know, how is this actually representing the real system we're trying to figure out the behavior? There's a little video of me, you know, really bored for if you looking to watch something. I talked about a real project that we calibrated a year ago, sanitary, for the city of Clarence Rockland. It's one that we talked about using optimization for calibration and machine learning. Quite interesting results. I had a lecture here that I gave almost like a year ago for teams. I was sort of if you want to take a look at it, and you know, this is the simulated results, and this is like the observed. You know, you try to minimize the gap between those two, and that's how we get the models calibrated. And you can never have like a perfected 100% calibrated. Sometimes we say this model is calibrated only for a 5-year rain event or a 10-year rain event. You cannot calibrate a model for everything. no model is like completely calibrated to represent all the different extremes and situations. I'm pretty sure that you're gonna have a lot of questions. I think we've covered a lot of these things in here because I need to go a little faster. After all, a lot of computation calculation is done by the computer. You want to make sure if you understand what's coming out of the computer because you make the decision. Okay, that's really because the computer cannot think. Computer is not able to. That's our. And there's a saying, all models are wrong until they're understood. If you don't understand what's kind of coming out of the model, you should assume that the model is wrong until you make sure that you understand what's coming out of the model. I was going to talk about, you know, in industry, and when you see the job ads, they say modelers, hydraulic modelers, structural modelers, who are not modelers, computers. We're engineers. You have a brain, you have a heart. A computer can never do that ever. Okay. Beyond modeling, there's optimization. My whole life, academic, is an optimization. Now I'm using it in sanitary systems. This is a pump station, 2 pump stations that we optimize. All pumps running, some of them off and on, and then some of them running variable speed, some of them at full speed, and how we get, you know, the energy or like the hydraulic, what's it called? The hydraulic performance of the system, how we fill the gaps and like improve in different, very different alternatives or like situations we're looking at. There is a video in here. I was going to talk about it, but seems like we're not going to make it. And it's after lunch. So if you're truly keen about it, you can watch that. Also, beyond modeling, as I said, there's optimization, there's stochastic modeling. Here's another latest work of mine that was published in late 2021, a Journal of Water Resources Management. We look at, instead of saying, okay, I'll put X1, X2, X3 in the model and I'll get Y1 or Y2. We say, what if X1 changes with this probability and X2 changes with this probability? What is the probability of Y1 to be this value or this value or this value? You know, so instead of giving the decision maker or the operator one solution, you're going to say, there's a 50% chance that this is going to happen to you, 10% chance that, so that they can act a little more resiliently. Is that a word, resilient? I don't know. But you know, they can be prepared for different types of situations. So that's, and through those 2 YouTube videos, it's so weird when I look at myself on YouTube. You can talk about, you can listen to the lectures and how the results transpire, and also you can find the publications. Some brutal facts. We want you to be really good at Excel data management times over. I think I have 1 or 2 more slides and that's it. ArcGIS. If you, I think a good percentage of you would be very familiar with scripting, coding. You know, it's something we don't really talk about it. We don't talk about Bruno, but Bruno's a big deal because if you know how to script, how to control Excel, or if you can link your code with a hydraulic model or any sort of model, then that's going to be a huge advantage there. Okay. After technical skills, we want you to be really organized because there's a lot of data that you're working with. You're gonna, and a team of other people accessing the same folders and the files and, information. There are some ground rules. This is how we use the information. Just, don't mess around with the files and whatnot. Patience and good communication. Because when you are the technical person in a project, everyone else, all other team members, they think you know everything. Like the designer, the project manager, the client, project support. Because let's say a hydraulic model has a lot of information in it. You're the hydraulic modeling engineer, so you know everything about the hydraulics. Everybody's asking you questions, so you got to be very good at communicating. And one thing that we really look at when we interview people, see like how they communicate. And obviously, most of you have advanced degrees in here. I was going to suggest, because it's a part of the slides that I usually give to the undergrads. Don't stop. I'm going to provide you with some more resources if you want to learn about hydraulics and stuff like that. Software packages. Obviously, Google is your friend. And you can watch my YouTube videos if you want to see more of me talking about hydraulics. A lot of things, calibration, optimizing, you can get a chance to talk about. SCADA, calibration, transits. Here are some resources for you to look at, because I have the time to talk about everything. 45 minutes or something. I'm already over. This is my LinkedIn. Let's get connected. Send your resumes if you want. Flip me your questions, send me your questions. And it's just, to start, to establish. I hope you're still awake. Or if you're not. Any questions for me? Doesn't have to be about this. If you didn't like it, you just ask anything you want. And if I can't answer it, I'll just be embarrassed. Yes.
Thank you for your nice presentation. I'm wondering if the company that you are working in actually does any risk management or risk analysis over this kind of infrastructure, like water distribution system?
Yes. Yes. Yeah, the different needs are usually dictated. Consulting, I mean, say it's a strange business, but this is, a specific, special type of business. Because when we get out of university, we talk about needs. This needs to be done. This is a fact. There is a knowledge gap. The university is working on it. Hundreds of thousands of dollars to support this. But when you bring that kind of statements to, I hope I'm answering your question, but I'm not done, you just keep. When you go to consulting, they're like, we're big. Unless they can make money with it, they're not going to listen to you. So strange. And what happens is, if what you're saying is communicated to them by their clients, they're going to do it tomorrow. If it's a real problem, you're killing people every day, but the clients are not asking for it, they'll be like, oh, nice. So I would say, so the answer is like, yeah, it's a little complicated. Risk management, usually in the realm of project management, it comes in. Absolutely. But if you want to establish risk management, you should raise awareness in their clients. You raise awareness. I don't know if I answered your question, but what was risk management in systems analysis, or like risk management in projects in general?
In terms of, for example, having any problem or disruption in any stricter of the infrastructure.
Yeah. Well,
For example, having
Ontario-
one pump station, for example.
you know, in Ontario. We, not very directly, but yes, we look at it, you know, some resilience, with some reliability. It is looked at, but bigger clients, like in the UK and the United States, they're also green to the issue. And not because of, you know, necessarily our engineers in the United Kingdom or the United States, it's because of their clients. Where in Canada, we're a little more like. But we're getting there. We're getting there. No problem.
I think we won't have time for further questions. The speaker will be available afterwards.
Okay.
General discussion, but I think some people might have to.
Okay.
So thank you, everyone. Let's give our speaker one minute of applause.
Don't forget to scan on your way out.
Yeah.